So, good afternoon, everybody. Welcome to today's colloquium. Our guest is Privatdozent Dr. Silvia Spezzano.
Noch nicht Privatdozent.
Noch nicht?
They need to approve my thesis.
Okay, because it's that. Anyway, about to become Privatdozent Dr. Spezzano. Silvia Spezzano is an expert in chemistry. She actually did her master's degree in industrial chemistry at the University of Bologna. The thesis on raw vibrational analysis of 15 NH3 in the 3 micron spectral region. And then she went as a pre-doctoral fellow to Harvard University for a few months. Then and the master thesis was in 2008. In 2013, she finished her PhD in physics, and this PhD was done at the University of Cologne with Professor Dr. Schlemmer, and it's on elusive molecules in the laboratory and in space. So you can see over the theme of her work, laboratory measurements and space measurements. And then she went first as a postdoc, stayed as a postdoc at the University of Cologne, but then she quickly went as a postdoc to the Max Planck Institute of Extraterrestrial Physics in Garching, also Munich in Germany, where she started 2016. Then in 2017, she became a Minerva Fast Track Fellow of the Max Planck Society. And this was between 2017 and 2020. And since 2020, she is now Max Planck Research Group Leader at the Institute, and her research is on the evolution and inheritance of molecules from interstellar clouds to planets using observations. This is also the topic of her talk. So I would say it's a pleasure to have you here, Silvia. Let's introduce us to the magic of chemistry in space.
Thank you. Can you hear me well? Thank you very much. It's a pleasure to be here. It's a beautiful sunny day. I had a beautiful walk to the Institute this morning, so it's really a pleasure. So yeah, we talk about the molecules in space. This is my expertise. I will try to take you on a journey going from interstellar clouds to planets and highlight as much as possible not only how fun it is to see molecules in space and observe them, but how useful they are to understand fundamental astrophysical environment and astrophysical properties. This is the outline of my talk. I will start with a brief motivation, of course. I will then talk about isotopic fractionation, and then I will move on to the physical and chemical structure of very early courses, so prestellar course, even before you form a ground prototype. And then I will talk about future plans. They are actually current plans. I call them future plans when they are not yet published, just to keep a bit of pressure up of myself. And in the future plans, we'll talk a bit about exoplanets as well. So I'm interested in understanding, as Ludmila was saying, how molecules are inherited, how they are formed, within the formation of a star. So here what you see, this is an artistic impression of the formation of a low-mass star, so a planetary system like our own. And indeed, there is quite some inheritance. Obviously, there are some energetic processes, like when you form a protostar, there is a certain grade of chemical reset, but there is some inheritance, meaning that there is some molecular chemical memory that is inherited from the prestellar cause down to the formation of planets. And the fun thing is that because the chemistry and the physics in these objects are very deeply interconnected, while we have fun studying the chemistry, we also get a lot of information about the physics and the physical properties of the objects that we are looking at. Talking about inheritance, the best example is the example of water. So water, while studying its deuteration of water in the solar system, in star-forming regions, and not only observations, but also a lot of modeling. By doing that, the community has been able to constrain that a large fraction of the water that we have now in the solar system, so 30 to 60%, has been formed and deuterated in the prestellar phase. So in the prestellar core, where our planet, our sun was afterwards formed. And this is what I'm showing you here. There is a direct connection from the prestellar phase down to planets. So there is some inheritance, actually direct inheritance from the very early stages. And I'm depicting here water as ice, because you can see it better, but also because it's the cold water, the water that is preserved during the formation of stars and planets. Hot water, warm water is lost in outflows, while cold water in the form of very thick icy layers on dust grains is the water that is finally preserved. So one of the questions that drives my research, keeps me up at night, not really, but is what else? What else is inherited together with water? We know that water, these ices do not only contain water, there are many other molecules embedded in the ices. That doesn't mean necessarily that they are also efficiently inherited. So I want to know what else is inherited, which is strictly connected to the question of how complex does the complexity of chemistry becomes in star-forming regions. So what is the level of complexity that we can expect that is even possible to be inherited in the process of forming a star? And then the next question is, what about other planetary systems? Now, as an astrochemist, traditionally, our community has been drawing connections from star-forming regions to the solar system a lot, which is great. It's very interesting. It's deeply connected with our own astrochemical origins. But we know now that the solar system is not the template for formation of planets. Actually, not at all. And as an astrochemist, the fact that we are entering this exoplanetary era, where we are finally able to connect the great diversity that we observe in the chemistry of star-forming regions, we can connect it with the great diversity that we observe in planetary systems. So it has a lot of potential, I think. And so I think it's fantastic that we can finally break free from these continuous connections to the solar system, or, well, it's great to have them, but we don't only want to, we are finally able not only to connect with the solar system, but also with exoplanetary systems. The only way to do that, the only way to answer these big questions that keep me up at night, is to work in a multidisciplinary fashion. This is what we do in my group. We have laboratory experiments, we have theoretical work, models, chemical models, physical modeling as well, and then we have obviously observations. And we use these tools, so theory, laboratory, and observations, to answer the same question. So this is very important, because without using a multidisciplinary approach, it's not possible to answer this question. There is always something lacking. Okay, so I will use these drawings throughout my talk to highlight what parts, what approaches have been used in the particular projects that I'm talking about. So let's start with isotopic fractionation. Now, isotopic fractionation is a set of processes, mostly chemical processes, but not only, that distributes less abundant isotopes into molecules. So isotopic fractionation is what redistributes, say, deuterium into molecules, substituting hydrogen, or it's when you substitute nitrogen 15 for a nitrogen 14, where nitrogen 15 is the rarer isotope. And understanding the isotopic fractionation of a very large scale is very important to understand the origin of the material, but also to understand the process itself. What I just showed you before with water, in terms of the inheritance that was traced by deuteration, shows that deuterium fractionation is, well, in my opinion, it's the best evolutionary tool that we have to study the inheritance and follow the inheritance of material. What you see here in this graph is the latest study of deuterium fractionation in the ISM. This was the new point added to the graph here. So you see that there is an order of magnitude increase in the deuterated water with respect to the normal water ratio in very young protostar, in this young protoplanetary disk. Here there are classes of comets. And so the fact that we added here also the young protoplanetary disk kind of confirms that there is this enrichment that is really kept throughout the whole process. So now that we've proven that this works with water, what I want to do is use the same tool, so isotopic fractionation, deuterium fractionation, but for more complex molecules, actually. And I want to use it for what we call complex organic molecules, COMS. Now, I don't know if there is any chemist in the room. Well, I'm the only chemist in the room. That's fantastic, because the complex organic molecules, so COMS for an astronomer, are any molecule with more than 5 atoms. So methanol is already plenty complex for us. Obviously, if you talk to an organic chemist or biochemist, that's not the case, but we're not going to see any DNA flying in space. So this is what we deal with. And so as I said, I want to use deuterium fractionation. So I want to track the evolution and the inheritance of deuterated COMS and COMS in general, in order to understand how are they formed, how are they inherited, if they are inherited, and also, as I was saying before, what is the maximum level of complexity that we can expect when we think about the budget that is inherited by planet? What actually can these early phases of star formation provide? Now, to observe molecules in space, we rely on laboratory data. We observe molecules mostly in the millimeter, centimeter to sub-millimeter wave range. So we observe the rotational spectrum. Now, the rotational spectrum is fantastic because it's unique for every molecule. So if you have 2 molecules that have the same atoms, but they are arranged differently, they have a different rotational spectrum. If you have 2 molecules that have the same structure, but different isotopes, they will have a different rotational spectrum. So you can really identify the molecules univocally. But you need laboratory data to observe these molecules in space. The spectra, the rotational spectra of COMS is complex, very complex. Here you have quite some lines. The job that we do in the lab is obviously recording the spectrum, but then we want to assign every line that we see to a set of quantum numbers, because what we need to observe these molecules in space is obviously the rest frequency of the line. But if we want to quantify how much of that molecule we are observing, then we need the Einstein coefficient, the energy of the levels, and everything that is only derived by fitting all of those lines with an appropriate Hamiltonian and so on. So it's complex for this molecule. So we started in our lab a systematic study of deuterated COMS. We have to give priorities to the ones that have that will have more power in terms of astrophysical tools, also the ones that can be observed, because it takes time to analyze the spectra. So this is the first project that we did. This is doubly deuterated acetaldehyde. This is one picture. It's actually a cute picture. I think it was done for a fact by Rat or something like that. Well, anyhow, this is a portion of one of our labs in a very nice light. So we did the spectroscopy. We analyzed the spectra, assigned all the lines, and we have observed it for the first time in space. This is an observation towards RS 16293. This is a very bright young protostar. Is basically the source where everybody in the field looks for deuterated or complex organic molecules. And this is fantastic. I mean, the PhD student was very happy to have detected a new molecule in space, but we want to make the molecules tools, right? So we didn't stop at the detection. What we did here was to compare the doubly to singly deuterated isotopic ratio, so the abundance of the 2 molecules for a set of COMS. So these are the only ones that have been observed with doubly and singly substituted D. And you see there are not many. A lot of work is necessary here. And you see that the ratio is within error bars, the same. Now, does this mean that COMS have been formed and deuterated in the prestellar phase like water? They are all inherited and we're done? No, obviously not. but it's a good step towards that. What we need is more molecules, and we need more sources. Just one protostar is not telling us anything. Concerning having more sources, we now have a large ALMA program that has been approved actually 2 years ago, and it's almost completely observed, where we observe 11 additional protostars to the one that I showed you before, and we selected those protostars in different evolutionary stages and also in different environments. So we are now able to study the evolution of complex organic molecules in a more statistical, meaningful way, and also to assess the effects of the environment. And aside from new sources, we also need new molecules. So the next project that I wanted to tackle was complex organic molecules containing sulfur, because we don't know much about the chemistry of sulfur in space. Sulfur is a fundamental ingredient in the formation of life, which is always nice to put in the proposal, but it's also interesting in terms of interstellar chemistry. We have a lot of fundamental open questions in terms of the pure chemistry of sulfur in space. So these are the big questions that I had when we started this project. So as you can see, this reflects the fact that we don't know much about it. So how, where, and when do they form? How are they inherited, if they are inherited in the formation of stars and planets? And how does this compare with oxygen-bearing molecules? Currently in the models, they assume that they do the same thing as oxygen-bearing comets, but this has not been compared with observations. So, what we studied is a laboratory study of the singly and doubly deuterated methyl mercaptan. This is the simplest sulfur-bearing comet. So this is methanol with a sulfur instead of an oxygen, and we deuterated here in the methyl group 1 time and also 2 times. Now this project, it's done now. We are about to submit the paper. It took us 2 years to understand the spectra, to analyze the spectra of just one of these 2 molecules. And getting the data took us a couple of months. It doesn't take long, but the analysis is quite complex. It took us 2 years. The good thing is that we've observed it in space. We have the first detection. Again, the first detection is towards Iris 16293, so the same bright protostar that I was mentioning before. We are about to start an observing campaign with the COMPASS data to have a more statistical view on the chemistry and the comparison of the chemistry of methanol, methyl mercaptan. Interesting thing is that we see a lot of differences in the deuteration of the 2 molecules, which highlight how much we don't know about how this molecule even forms. Okay, so this was really, really nice. And it was quite a big pat in the back for my postdoc that has been working on this for 2 years. 2 years, it's a long time. Yeah.
Can I have a quick question?
Yeah.
Can you also deuterate the other end of the molecule?
Yes.
So that would give you a different spectra. But if you say the other 3, is that rotationally? So I'm looking for the isomers. Does it depend on which of these things you deuterate?
In terms of which spectra you see?
At which position of the molecule?
Yes.
I think.
So if I deuterate here, it's another spectrum.
Yes.
If I deuterate here, it's another spectrum. One single deuteration is 1 molecule on the CH3 group here, but it tunnels. Mm-hmm. So this is what makes the spectroscopy complex, because you have 1 symmetric and 2 antisymmetric conformers. They all contribute to the same spectra, and they push their level away. So there are a lot of resonances, which makes the spectra a mess.
Let's say the deuterated molecule on the other end.
The spectroscopy of that has been done already, and the molecule has not been detected. We know from methanol that the deuteration on the methyl group is more abundant, so it's more prominent than the deuteration on the other functional group. Yeah.
So it has chemical reasons why this is so.
Yes, yeah.
Thanks.
So the CH3 group, functional groups, this is important. Also, I'll tell you a bit more soon. The deuteration of which functional group is very interesting and important to track, because it really gives you a tag on the molecule, and it gives you more information when it comes to understanding how they form. Especially for molecules like this that most likely form on the surface. And so it's really like a little Lego Stein that you put together. Okay, so we detected this molecule in space. That was really good. We are now working on deuterated metal format. So here we have, this is metal format, and here we are looking for the molecule where there is one deuterium on the metal group and one here on the ester group. This here, okay? So this is a project that's much more simpler than what I just talked about. So it's not going to take 2 years. A master student is working on this, and I reckon that by the beginning of next year, we'll be able to search for it. What you see here in black is a small portion of the spectrum, the recorded spectrum. We observe over 400 gigahertz. So here you have, well, way less than 400 gigahertz. And at the bottom, you have our model, and you can see that it works quite well. We still have to assign quite some line, but the pattern looks really, really good already. We are also working on methanol, but I decided to take away the slide apparently. So there are many challenges in this project. So sample preparation is definitely one of that. Here you see Haley, my fantastic postdoc, that is working on preparing the sample for metyl mercaptan. Now the molecules that we studied are not solved, so like that. We need to either come up with a fantasy method to make them in the lab, or we ask organic chemists to prepare them or prepare precursor for metyl mercaptan. Because it's a gas, we could not have our collaborator in France ship a sulfur-based gas. It would have done it. He has shipped us quite some stuff, but that was impossible. So he made a precursor, and then we did the synthesis in the lab. Sample preparation, but we need sample purity, basically. The purer the sample, the better it is. Long scans, it takes 3-4 weeks to scan, work 24/7, which we can. I mean, it's automatic, but we need to refill our cell every day, at least. It depends on the project. So here you see my kids that I drag with me in the weekend to the lab when we need to refill the cell. They're very patient. No kid was harmed in the making of this presentation.
I thought this was a collapsed researcher there.
Yeah. And then models, last but not the least. If we want to make these molecules astrophysical tool, we need to rely on models. So all of these abundances and ratios that we observe, they're fantastic. We observed it in many sources. It's also fantastic, but they stay as numbers if we do not use models to draw the link together. So models are incredibly important. The chemistry of methanol itself, it's still puzzling. Well, the deuteration of methanol is still puzzling. We still don't get it right to match what we observe. So it's going to take a lot of work to keep the models updated and actually up to date, yes, with what we observe. But it's definitely fundamental to answer those big questions. Now, just to summarize this part of the talk, in my group, we do laboratory spectroscopy of molecules of astrophysical interest and then detect them in space. All of the observations I showed were done with ALMA. And the overall goal is to understand how they are formed and how they are inherited in the formation of stars and planets. It's very important here that we do both of this. It's very important, actually, that the motivation of the project comes, say, from the same big question, because, as I said, metyl mercaptan took 2 years. It's worth because we prioritize based on a set of very specific questions that we want to answer. Now, obviously, everybody can have their own priorities, but if you don't have priorities and you use 2 years to study a molecule that has no chance to being detected in space, it's fundamental science, it's going to be great, but it's not going to help us in understanding this topic. So it's really good that we have this multidisciplinary approach to the same questions. So going back to the picture of star and planet formation, I want to talk now a little bit about the earliest stages in star formation, which are prestellar cores. As a reminder, this is where the water that we are drinking today, where 30 to 60% was formed. So I spent a lot of time in the last decade studying the chemistry and physics of this object. As I said, the chemistry and physics are very deeply interconnected. So while I study the chemistry, I also learn about the physics of the object. Plus, molecules are not homogeneously distributed in star-forming regions and in prestellar cores. So when you use a molecule to measure the density or the temperature, and you know the chemical structure, you can use different molecules or different excitation lines to get the temperature and or the density at different depths. And so getting an idea of what is the three-dimensional structure of your core. So it's not just the chemistry, it's also the physics. So now, I don't know if you have your favorite object. I do. It's this. This is L1544. It's a prestellar core in the Taurus molecular cloud. This is an artistic impression of the core. I work with very dark objects. They don't do cute pictures. So I have to ask amazing people in the field that know how to draw. I have to ask them to make it cuter. So this is L1544. As I said, prestellar core, there is not a protostar yet, but the material is accreting towards the center of the core, so it will form a protostar very soon, whatever very soon means for a prestellar core. So by studying it relentlessly for almost a decade, we have derived the chemical structure of it. And you see here the four molecular peak that we defined in L1544 based on where the emission peaks of the molecules are. We found these four molecules. These are the actual maps done with the IRM 30-meter telescope. And the segregation of these molecules, so the different spatial extent, is somehow related, in some cases related to the physical structure of the core, but in some other cases is related to the structure around the core, so where the core is embedded. And this is the case, for example, for these two methanol and carbon chain molecules in very different places. And this is because the southern part of L1544 is almost bare naked looking at the interstellar radiation field. It's because the core is located at the edge of the cloud, at the end of a filament. So there is not much gas that protects it from the interstellar radiation field. And this keeps a very active carbon chain there. So carbon is not locked in CO here, but it's making a lot of carbon chains. Well, when you move towards the north, carbon has the quiet to be locked in carbon monoxide and form then methanol. So, and this is, we've studied this also in other cores, and this is all due to the density structure basically around the core. Now, why do we care? But before I go to the next step, why do we care? We care because these molecules are moving towards the center, so this core is very slowly infalling. And while moving towards the center in the way of forming, in the process of forming a protostar, it's the molecules freeze onto dust grains because the temperatures become lower, the densities become higher. So all of the molecules that I map around the core are finally the molecules that are going to be in those ices, in those thick ices that we've seen that can be very efficiently inherited in the formation of planets. So if I want to know what is the budget that is at all available for forming planets from the prestellar phase, I need to make these kind of maps. I also studied the nitrogen fractionation in this core, and here we could see that there is, so this is a map of HCN, so it's the ratio between HCN with nitrogen 14 with HCN with nitrogen 15, and we see a strong decrease of this ratio. So there is a local increase here of nitrogen 15. And this is also a consequence of this more effective illumination from the interstellar radiation field in the south of the core. And this had already been seen in protoplanetary disk. This is a paper from Pierre Leblanc in 2019. What you see in red is the decrease of the 14 to 15N ratio in HCN in a protoplanetary disk. And it decreases very steeply when you go towards the star. So in this case, the decrease of the ratio is a consequence of the illumination of the UV photons from the star. What we showed here is that you don't need the star to do that. I mean, a star would do, but also just the not even or uneven irradiation from the interstellar radiation field is enough to change the 14 to 15N ratio. And once again, this is important because if you want to know what is the nitrogen isotopic budget that comes from prestellar cores, you have to look at where the prestellar core was, because the environment will play a significant role. And this is linked to the many open questions that there are in terms of the nitrogen 14 to nitrogen 15 ratio in the solar system bodies. We use molecules also to get to the physical structure of the prestellar cores. What we did here with one of my postdocs was to do observation towards the 4 molecular peak in 1544 of different excitation lines of 3 different molecules. And we did a very detailed study with non-LTE radiative transfer modeling to learn about the physics of the emitting gas. And what we figured out is that methanol, the fantastic volumeter, it measures the volume very well. Densitometer, what word I was looking for. Anyhow, so it measured the volume, so the volume density very well. And so by looking at the methanol, we were not able to reproduce the lines unless we added this density bump here. This is the classical density profile that we use for F1544 that works for any kind of molecule. For methanol, we needed to add this little density bump. It's not little, I mean, it's significant. You see, this is a logarithmic scale. But it was constrained by observation, so we did all the due diligence that we needed to do. But what we saw, basically, even if we were using single-dish observations, so we were using not a very fine angular resolution, we could still, through the molecular emission, we could still look at these density enhancements that we think are coming from the accretion from the filament onto the core, which doesn't have to happen in a smooth way. I mean, we see this beautiful smooth map, but nothing is smooth, especially at smaller scales. So the beauty of this work is that we could really see it just by observing methanol with a single-dish telescope. Now, talk a lot about 1544, but we want to see other prestellar cores. There are many available. This is a very short-lived evolutionary stage. So we are now hunting for new prestellar core with APEX. It's a beautiful telescope. And we do that by looking at N2H plus and N2D plus. We found a couple, and I want to use one of those just to show you again the power of molecular emission. So these are the lines that we have observed towards this prestellar core here. It's called RS16-293E. There are 3 rotational lines of N2D plus and 2 of N2H plus. The red curves that you see are the results of the non-LTE modeling that I did. And in order to reproduce these lines so well, I had to use like an infall velocity profile, a constant abundance, and then we use the physical structure of the core derived by Herschel observations. And it worked quite well, but the lines are very sensitive to little changes. And I want to give you an example. So this is the best match with my model for the 3,2 and 5,4 lines of N2H plus. And this is done by using an infall velocity profile and a constant abundance of the molecule. If I keep the constant abundance of the molecule, but I take away the velocity profile, so assume the core to be static, the 3-2 doesn't work anymore. So it really needs the infall. And this is a very small infall. I just add in the outer part of the core, so a radii larger than 3000 AU, I add a velocity of alpha kilometer per second. It's not much.
These 3 peaks are this
This is the hyperfine structure of the line. It's the same rotational line. So yeah, so the velocity is necessary, but it doesn't really affect this line here. However, if I keep the infall velocity profile, but I add a little bit of depletion of the molecule towards the center of the core, which we expect, the center we reach very, very low temperatures, very high density, the molecules will eventually deplete, meaning that they freeze onto the dust grains. This line doesn't really care, while this one decreases quite fast. So by using this multiple line observation of these particular molecules, of these particular lines, so if you choose your molecules and lines wisely, you can really get very precise information about the structure of the emitting gas, even when the structure is smaller than your observing beam. Because if you think about it, we are observing through a density and velocity and temperature profile anyhow, even if we don't do a map, right? So this was very cool. So future plans or current plans, actually. So I will tell you a bit about some projects that are not yet finished. One is a project that was approved by the DAAD in Germany that allows me to work with Doris Artsumanian. Doris is a fantastic scientist now working in Japan. And what we want to look at is how the filament collapse in forming cores. We want to do this with synthetic observations in order to then compare with actual observation. We actually want to use the synthetic observations based on models that they have in Japan. In order to guide the observation, we want to see what are the molecules, what are the molecular lines or the molecules that are more sensitive to these, to the fragmentation and the collapse. We are also looking at signs of ambipolar diffusion in prestellar cores. I think we got some, but it's still very preliminary, so I will not show anything, but it shows again the power of high resolution spectroscopy done with telescopes. And then we want to, like many other people, we want to explore the influence of cosmic rays on this fragmentation by adding in the simulation that the people in Japan have. Another thing that got my attention in the last couple of years are exoplanets. As I said, exoplanets we are moving towards detecting them, studying their atmosphere. This is fantastic for an astrochemist. It's not easy, and I don't have to tell you guys this, but going from the observations to abundances is quite tricky, and it takes a lot of information inside. It's not an easy jump. So one thing that we started in my group, still keeping in mind the multidisciplinary approach, is a laboratory experiment to look at the pressure broadening and pressure shifts for sets, a couple of molecules that are important for exoplanetary atmospheres. This is a summary of everything that is in the catalog at the moment in terms of main molecule and the broadener. It looks complete, but this is not the full picture. For example, for N2O, all of the measurements that are in the databases are not from N2O, but are from CO2. There are just two measurements of N2O, like two lines actually, done, I think, just with helium, and they, in the literature, done in the laboratory, and they don't agree. So we are working now, so our first project is to work on N2O. We will then move to SO2 very quickly. I have a PhD student that just started, and she's only going to work on these experiments. So hopefully, very soon, I will have also some result, or my student can come and present their results. When it comes to observation, this is quite a busy slide. One thing that really got my attention in the last years was the detection of the carbon-13 carbon monoxide in Super Jupiter. And this is this paper here from Yapeng Zheng. They detected the carbon-13 CO and they derived this ratio, and I have here the solar system and the local ISM isotopic ratios here. So it looked like it was an enriched carbon-13 CO towards the Super Jupiter. And these were measurements done with Symphony at the VLT, and you see here the spectrum, the resolution is all right. Although recently, Yapeng published a paper on the same object, observations done with a different instrument at the VLT. This is CRARES Plus, much larger frequency resolution, and now she derives about 8. Now, who was right? Was she right in the past? Is she right now? In the paper, obviously, she discusses about the fact that these two numbers don't agree at all. There is not a conclusive reason. There are a couple of things that go on here. There is, I think that doing a study assessing how much the frequency resolution of your spectra affects the final result is something that it's necessary. Also, when you have a very high spectral resolution, your frequency or wavelength coverage is much smaller. That means that you see it with better resolution, but you see much less lines. How does that affect the final numbers that you get? And then there is obviously the variability of the planet. Should we expect some variability? Are we even looking at the same object in terms of fractionation of or ratio of 12 to 13 CO? These are all very interesting questions that we hopefully will address in the future. Something that we did last year was, together with a few people here, we submitted a paper to observe the same super Jupiter here, so YSS B, with gravity. Gravity is collects the light from 4 telescopes at the VLT, and then does interferometric observations. Beautiful telescopes are cool. And this is our gravity spectrum. So we do not have yet a 12 to 13 CO ratio, but this is what we want to see. This is the same wavelength covered by Symphony. You see the 3 CO bandheads here. So something that we wanted to explore with this project is gravity the instrument, because it's very sensitive. It has been just upgraded, so it's going to be even better now than what we see here. Is this the instrument that we can use to make a systematic study on several exoplanets to derive the isotopic ratio in a, say, time feasible way? Let's see what the results of the analysis will be. This was already, I think it was 3-4 hours of observations in total. It's hard to tell because they found it in different nights and then you lose track of what actually was the time spent on source. But yeah, I mean, the spectra look nice. I mean, this is what Ludmila was telling me. Coming from the ISM, this is very, very, very noisy to me. So, to conclude, the chemistry and the physics are deeply interconnected. This is obviously also the case in exoplanetary science, but definitely in the interstellar medium in star formation. Molecules are very powerful, not only to chemistry of star forming regions, which is very interesting, but also to follow and understand very fundamental processes like star and planet formation. And future will bring lots of fun. And obviously, I want to thank Paula, our director, my group members, and the Max Planck Society. It's always very generous with their funding. And thank you all for your attention.